So good. All right. So you can ask, some patient is exposed to 600 micrograys, so 600 millionths of a gray of X-rays to the gonads. By the way, before answering this, what would their dose equivalent be if they got 600 micrograys of absorbed dose? Ignore tissue weighting factor. I said dose equivalent, not effective dose. Dose equivalent. Okay, this one. So it's a 1-to-1. So if they got 600 micrograys of absorbed dose in X-rays, what's their dose equivalent? 600 what? Not 600 micrograys. 600 microsieverts. Okay. It's a 1-to-1 relationship, but the unit is different. Okay, the unit used to express dose equivalent is different than the unit used to express absorbed dose. The only reason they're the same, 600 micrograys and 600 microsieverts, is because we're talking about X-rays. If we were talking about alpha radiation, the dose equivalent would be much different in sieverts than the absorbed dose. Okay, it's kind of tricky with X-rays because X-rays, everything is a 1-to-1 relationship. Okay, 600 micrograys of exposure is 600 micrograys of absorbed dose is 600 microsieverts of dose equivalent. Okay, so there's a 1-to-1 relationship all the way through as long as you're talking about X-rays. Yeah.
Probably already know the answer to this.
Good.
So when they were discovering the X-rays, was there a conscious realization that these are more harmful, so let's not use those, let's use X-rays instead?
Not immediately.
So, they're like, oh, we have alpha rays, let's use those to make images.
No, because they knew about alpha and beta rays, but they didn't pass through anything. X-rays and gamma rays were the only ones that could pass through things, right. And gamma rays, for important reasons, are not easy to make. Okay. So X-rays were the only thing that was easy to make and could pass through things. Okay. Yeah. I'm looking in my physics notes here about where I stuck this stuff for you guys, and it's actually on this note, the packet that I gave you called Radiation Safety / Physics Study Points. On the second page, number 8, F, and G give you these weighting factors, and H and I give you the formulas for calculating effective dose or equivalent dose and effective dose. So you have these in your notes in multiple different spots. So number 8 and the subcategories 8F, G, and I. So 8F through I. We'll give you all of that in the physics notes. Okay. Anyways. Because I know when I remember learning this the first time and going, oh, there's a lot to learn, right? It's a lot of units. I got to remember a lot of ways that the units are calculated. It's not as hard as it might sound, but you're just going to have to continually expose yourself to it. Like it's going to be sort of a memorization thing, right? You had to learn about how to take basic measurements. Like if you know how to use a tape measure, someone had to teach you how to use that tape measure, right? I'm trying to teach you how to use this tape measure. Okay. Right. What are we missing something? Last week, yeah. There should be some spares. Hang out till we take a break. If somebody needs a copy of this, I should have some spares somewhere. But it looked, I know it's a long ways away from you guys, but it looked like this. It said Physics and Safety Study Points at the top of the page. I give my little paragraph disclaimer about this is helpful, but take it with a grain of salt. Okay, anyways. So to recap. Exposure, measured above the object. Absorbed dose, inferred from exposure, okay? Once you know the absorbed dose and you know the type of radiation, you can tell me the dose equivalent, okay? Once you know the dose equivalent and you know what type of tissue it was, you can give me the answer to what is their effective dose, okay? So this was 600 micrograys to the gonads. So you just take 600 microgray and you multiply the number 600 by the number for gonads, which is 0.2. So 600 times 0.2 is just 120, okay? So it becomes 120 microsieverts, And this would be different. Like, let's do it real quick. If this is, they didn't put this in here, but let's just do it real quick. If it is skin, cortical bone or skin, where the laser pointer's on right now. So just take 600 times 0.01. Tell me what you get. I should have known that answer. I plugged it into the calculator though. What is it?
I was about to use the calculator.
You didn't need it, did you? No, but that's okay. I like the calculator. Even if I can do it in my head, I like the calculator because it lets me know that I'm not wrong, right? I can convince myself that my internal calculations are right, but the calculator helps me know that. Do you guys get the answer? What is it? 6 microsieverts, right? So if they got if the effective dose was to the bone, and they got 600 micrograys of dose, then it would be 6 microsieverts of effective dose. If that same amount of dose was to the gonads, it ended up being 120 microsieverts of effective dose, which is more, right? 120 is bigger than 6, okay? And that's the idea here, is that now you can relate different tissues to one another and talk about how much more harm is caused to the two different tissues, okay? Less harm is caused, at the same amount of radiation given to the bone or given to the gonads, it's going to cause more harm within the gonads than it will to the bone, okay? And there's important reasons for this, which we're going to get into in later lectures, but the starting point is that it's true that the gonads are more sensitive than other body tissues. The number for them, the radiation tissue weighting factor, is a bigger number. So the smaller that this tissue weighting factor number is, the less sensitive that tissue is. The word we like to use is radio-resistant. Skin and bone are more radio-resistant than the breast. Okay, the breasts are more radio-resistant than the gonads, and the gonads are the most radio-sensitive or the least radio-resistant. Okay, so just to kind of round this out, proper use of these units, when are they appropriate? Well, the coulomb per kilogram, that thing about the air kerma and the gray in the air, that's a physics unit. That's telling you how many things, physics deals with movement, right? So it's telling you how many things you're causing to move around by putting an amount of energy in the air, how many ionization events you're creating in the air above the patient, coulomb per kilogram. It's appropriate for describing the X-ray beam as it leaves the X-ray tube, so that unit can be used to express the intensity of the X-ray beam before it's interactive with anything. The gray is another physics unit. It can describe air kerma or tissue kerma, how much energy is deposited into the tissue or the air, some amount of mass. There's no, at the atomic level, at the atom level, there's no difference between air in the room and your body, okay? Your body's made of solids, liquids, and gases, where the air is just a gas, but the atoms aren't different, right? The air is made up of nitrogen and oxygen, and you're made up of similar things, right? For example, you're made up of a lot of oxygen, right? You're 75% water. Water is H2O, right? 2 H's and 1 O, right? That 1 O makes up a lot of your body. Good big percentage of your body, that one oxygen, those oxygen molecules. So it's the same thing. The X-ray beam doesn't care if it's ionizing your body tissues or the air in the room, so the gray can be used to talk about both. But it's just a physics unit. It's telling you how much energy is deposited, it's right here, how much energy is absorbed or deposited into any substance, air or tissue, doesn't matter. Sievert is the unit of biologic harm. Right? We use the sievert for dose equivalent. And remember, dose equivalent takes into account the absorbed dose times the type of radiation. Effective dose takes into account absorbed dose multiplied by the body tissue. Now, you might still see so let me focus on just the two, the gray and the sievert, for right now. focus on the gray, talking about absorbed dose, and the sievert, talking about effective or equivalent. But I'm gonna put biologic harm. Okay. Those are SI units. Okay. I'm going to call them British units. Okay, the British or standard units are going to be the other type. So the gray is the unit for absorbed dose in the SI system of measurement, the metric system. Okay. In British units, the rad is the equivalent type of unit. Okay. I'll talk. Just let me get this up, and then I'll make some more notes. The sievert is the SI unit of biologic harm. In the British system of measurement, it's a unit called the rem. Okay? Now what's the relationship here? One gray is 100 rads. Okay? And one sievert is 100 rem. So it takes 100 rads to equal one gray, 100 rem to equal one sievert. The gray and the sievert are big units, okay? The rad and the rem are small units. Again, this is just like converting kilometers per hour to miles per hour, right? There's not a one-to-one relationship there, okay? There is not a one-to-one relationship between gray and rad. The way the book would like you to remember this is how to convert from millirem to microsievert. And that's a 1 to 10 relationship, okay? The reason for that is because the rad, the rem, the gray, and the sievert are all pretty big units, so often we find ourselves using milligray, microgray, millirad, microrad, right? We find ourselves using these small numbers. Where this is going to become important is the personnel monitoring companies, the people who give you these badges, okay? The companies that produce these badges, when they produce their badge reports and they give you their badge reports, they're going to report your dose equivalent, okay, in millirem, not microsieverts or millisieverts or anything like that, okay? They're not going to put it in the unit of sieverts, even though that's what everyone else is using now, okay? That's what we use in modern medicine and stuff. We use the metric system. The badge companies are all still used to reporting things in the rem unit, okay? In the British units, okay? And it's not a one-to-one relationship here. So the way to do this is to convert from millirem into the familiar unit for you of microsieverts, okay, or just the unit of sieverts, right, to convert from one system of measure to the other, multiply by 10. So whatever the number is in millirem, multiply that by 10, and that will be your number in microsieverts. If you wanted to convert to millisieverts, it'd be multiplied by 100, right, because there's a 100 to 1 relationship between rem and sievert, 100 to 1 relationship between rad and gray. But that's it. 1 millirem of exposure equals 10 microsieverts. By the way, the one thing I can credit the British system for doing is having decent acronyms, right? RAD stands for radiation absorbed dose. It's easy, right? It tells you what it is, right? It's the absorbed dose. REM stands for radiation exposed man, because it's, the patriarchal, I guess, right? Okay, good. Well, not good, but that happened, right? So REM, radiation exposed man, okay? But it's easy to remember, right? They're just an acronym, okay? These are not as easy to remember. You sort of have to practice them a little bit because they're not an acronym, they're a name, okay? But there you have it, right? The gray in SI unit is absorbed dose. In British units, it's the rad. In SI units, the sievert is biologic harm. And in British units, it's the rem. And again, 100 to 1 relationship between the two. So as this says here, to go from millirem to microsieverts, 1 to 10 relationship. Okay. That's how we'll use these units. There's a couple last ones to get on the table here. These last units deal with radioactivity. Okay, so these first ones dealt with mostly, as we talked about, exposure, absorbed dose, equivalent dose, and effective dose. These 4 different ways to measure. But maybe you just want to know how radioactive a source is, not how much it's exposing anybody to, but how radioactive it is. Okay, so the unit that we'll like for that is going to be called the becquerel. Okay, and named for one of the early people who worked in atomic physics, Henri Becquerel. But a becquerel is 1 decay event per second. So if a radioactive source is spitting out 1 particle per second, then it has a radioactivity of 1 becquerel. Okay? If it's spitting out 2 particles per second, then its radioactivity is 2 becquerels. Okay? A becquerel is a decay event every second. Each decay event can either be the emission of an electromagnetic wave. What were the electromagnetic waves called when they came from radioactive atoms? Not X-rays. What were the 3 types of radioactive discharges that came out of an atom? We had alpha, beta, gamma. Gamma rays are the electromagnetic wave coming from a radioactive decay. Okay? So a radioactive decay event can either be an alpha particle, a beta particle, or a gamma ray. Okay? One of those 3 types of decays happens. Okay? That's a decay event. That event has a place in space and a time that it occurred. We talked about half-life of the radioactive elements last time, right? We talked about some have long half-lives, others have shorter half-lives. We measured the amount of radioactivity. So remember, a half-life was the amount of time it takes for the radioactivity to decrease to 1/2 of its original, right? We measured the radioactivity in units of becquerels. That's the idea. Okay. So just a quick summarization table here, right? The gray, used for exposure and tissue dose or absorbed dose. The sievert, used for dose equivalent as well as effective dose. The gray for exposure can tell you energy absorbed in air. The gray for tissue can tell you energy absorbed in tissue. The sievert can tell you biologic harm. And the becquerel can tell you how many decay events are happening, basically the amount of radioactivity some substance has. Okay, so if you see something expressed in becquerels, you know it's a radioactive source. You know it's telling you something about its radioactivity. And you know now that the becquerel is a single decay event per second. Okay, I want to do, that's a lot. Let me see here. Yeah, no, let's go through that and then we'll take a break. Okay. So let's keep going. I want to go down to putting these units we've learned into use now. And so what we're really going to need to know is, what are our limits? How do we stay safe, right? So now that we know what the units are, let's see how we can use them. So the first thing to do is, and notice what we're talking about, dose equivalent limits, okay? So what is dose equivalent taking into account? What do you need to know the dose equivalent? How much was absorbed, okay? And what's the one other thing you need to know?
What
Type of radiation, right? Now the type of radiation we're dealing with is X-rays, so the absorbed dose is equal to the dose equivalent, okay? So as long as you know your absorbed dose, you'll know your dose equivalent as long as you're working around X-rays. If you become a radiation physicist and you work around any other type of radioactive materials, then that changes, okay? But as long as we're in the X-ray field, it's a 1-to-1 relationship. So now we're going to be able to talk about, we're exposed to radiation as an X-ray tech. We get an amount of exposure, which implies an amount of absorbed dose, which implies an amount of biologic harm, okay? Now we need to know, because we know that X-rays are harmful and we're exposed to some of them, okay? and some of that's absorbed into us, and some of it causes harm. We need to know, what are our limits, okay? We have limits. That's the important thing, right? We are not at the beginning of the, when this field was created. This field's been around for well over 100 years by now, and lots of people have figured out how much exposure causes harm, okay? So we want to stay well below that. But we didn't start off knowing that, right? Lots of people had to figure this out. Last class, you learned about Clarence Daly being the first person to die from this, and many people after him. Anyways, so here's a quick history of this. In 1902, you guys hopefully remember the dentist named William Rawlins. His statement was, you should limit your amount of exposure to the amount that would cause fogging on a piece of photographic film over 1 day. So if by the end of the day, your photographic film became fogged, keep it near you while you're working, right? Your photographic film became fogged. He said, all right, you had too much exposure that day, get less the next day, okay? Notice you couldn't tell partway through the day or anything like that, right? Sort of similar, right? We give these badges back quarterly, okay? So we don't know how much we've received until we've gone a couple of months with the badges. They're sent to the company and then given back to us. It's sort of a retroactive process, right? Similar in this case, yeah? And in fact, he used pieces of photographic film and not these badges anymore, but badges were commonly film badges. They actually had a piece of photographic film in them that would get fogged with increasing exposure. Enough to fog a film in a day is about 100 millisieverts per day. Keep that in mind. This is the first recommended safety, 100 millisieverts per day. Okay. 1925, Sievert, the person Sievert, recommends 10 milli of himself, 10 millisieverts per week, 500 millisieverts per year. How much would that be? Go back to this first one. How much would that be in a year?
Well, if it's times 1, right?
Yeah. Yes. So, so we're already in dose equivalent units. So we're already in sieverts. So, 100 times 365. 3,650, right? 3,650, or 3.6 sieverts per year, roughly. Okay, 3.65 sieverts per year. Go to 1925, and they're recommending limiting that to 500 millisieverts per year. Not 3.6 sieverts per year, but only 500 millisieverts. So half of 1 sievert per year. We've decreased it roughly 6 times by now. 7 times, okay? So we're decreasing now. We're saying, all right, 1925, we got our stuff together a little bit. People have started to die. 1902, Clarence Daly was still alive in 1902. So we didn't even have our first radiation-caused death yet. He died in 1904, okay? So, but by 1925, people are dying. We want to know, how can we stop this? We know about time-distance shielding, okay? Cardinal rules of radiation safety. And so we get this recommendation. U.S. Advisory Committee on X-ray Protection Forms in 1931 recommends cutting this in half 5 years later. Recommends, doesn't have any, there's no, you have an advisory committee, you have no regulatory body yet, though. That's the problem. You have recommendations, but you have no one saying this is the rule now, right? This is our regulation. You get fast forward all the way to 1959. Okay, you get the National Council on Radiation Protection and Measurements, or the NCRP. These guys are the ones who now they're a council. Councils can't force anything. Okay, a national council is just a group that does studies, does experiments, and makes recommendations based on their studies and data and experiment. Okay, this is post World War II, so we've got our the aftermath of the atomic weapons to use as data. Okay, we don't have Chernobyl yet, but we have some data based on experiment as well. During the whole lead up through World War II, they've got a bunch of experiments, like the Manhattan Project with dealing with building these atomic weapons, right? So we learned a lot about that. Okay, in fact, several people died in the the experimentation and building of those atomic weapons because of radiation exposure. So we're learning things, and that's just in the U.S. We're learning things up by now. So by 1959, we've got some studies done, we got some data, we know some things. The NCRP reduces the limit to 50 millisievert per year. Okay, so we went from 3.6 sieverts per year down to 1/7 of that, and from that down to 1/10 of that second decrease. Okay, so we went from a lot to less to a lot less. Okay, which is, it comes out to about a millisievert per week, or 0.2 millisieverts per day. So 0.2 millisieverts per day in 1959 compared to 1902, where 100 millisieverts per day was supposedly the acceptable limit. You can't fault Rollins, right? You can't fault him. He didn't have much to go off of, right? All that they had to detect radiation were these photographic plates, okay? And that's what they used. They used what they had, right? We get better and better detecting devices and more data, and then we can make, more accurate recommendations. And so, all right, so yep, 1 millisievert per week, 0.2 millisievert per day. 1991, the International Council on Radiation Protection and Measurements, which is just the equivalent of the NCRP, but for everyone in the world, recommends decreasing to 20 millisieverts per year, but this is not changed. Okay, this was never changed. The U.S. maintains the 1959 recommended limit of 50 millisieverts per year, and that has not changed since 1959. Okay. Today, radiographers and everyone working with radiation is limited to 50 millisieverts per year of dose equivalent, and that has not changed since, again, 1959. Okay, and there's no prospects of it changing now. It's a safe limit, right? Where we can stay below that. Most, if not all, professionals can stay below that, and it's such a low dose that you don't see any adverse effects by people who get anywhere near that dose. So yeah, you want to know maybe how much you do receive. Practicing radiographers average about 3 to 5 millisieverts of dose equivalent per year. Okay, so this is your expected actual occupational dose of radiation. Okay, it's not a lot. We're going to learn later. You might not know what 3 to 5 millisieverts can do. I told you 1 gray, meaning 1 sievert, can cause death, okay, but that's to the whole body, okay. 3 to 5 millisieverts that you receive on average in a year is, 1, a very small amount, okay. 2, it's not to your entire body, okay. These are partial body doses, right, and that matters. That matters how much of your body is irradiated. This is less than the 1/10. This is less than 1/10 of the occupational limit, right? The occupational limit is 50 millisieverts, and if you're at 5 millisieverts, you're exactly 1/10 of that. Okay. This is a very safe margin. In fact, if you look at the guidelines recommend that anyone who occupationally receives more than 1/10 of the occupational dose limit is required to wear dosimetry badges, okay? You don't receive more than 1/10 of the occupational dose limit, so technically, there's no actual requirement for you to wear dosimetry badges. Now, how would we know that unless we put dosimetry badges on you, right? So you still have to wear them. That's the idea, right? You don't receive enough to have to wear them, but we can't know that unless you wear them. So you got to wear them. That's the point. But that was a very good point made to me by the state inspector when they come by, is that we don't receive anywhere close to the occupational dose limit. Okay, we receive so much less than that it's almost where we shouldn't have to be monitored. But limited techs are one thing, right? But radiographers working in cardiac medicine and interventional radiology, those kind of things, they receive a lot more, so you should probably closely monitor them, okay? And because we're so similar, such similar groups of people, right? Ex-limited techs versus the fully licensed radiographers, we're just going to monitor everyone the same. That's the idea, okay? But yeah, there you go. We're doing a safe job because the amount we receive is so low. Why is it low? Because we've learned a bunch, right? We've learned about time, minimizing time, maximizing distance, maximizing shielding, Our structural shielding in our rooms is just fantastic nowadays, right? We have our primary walls and secondary barriers like our control booth, right, that keep us safe during exposures. This is why our exposures are so low. In fact, your badge reports come back almost always listing an M or an N in your exposure received category. An M means minimal and N means negligible. Different badge companies use this different notation, but both of those things mean the amount the badges pick up is so low that it can't be measured and listed on your report. Okay, it's that low. So they basically are calling it zero. Okay, so very low, very safe, and it's because of all these safety practices that we have.
So, Alex,
Yes.
so there's not an accumulation of that low, there's not a number somewhere floating around, even though, because it's so low, they don't. what I'm
No,
saying
no,
is
they don't.
Cumulatively,
Right.
that really low number just doesn't, it
You're
just
thinking
shows
add-
up as a zero.
Right, but you're thinking add that tiny number up over a long time and maybe
Yeah.
it becomes something. That's true, but it's so low that it's not reportable, so they call it zero. So
So-
you can call it zero
So
too.
if you're in the business for 20 years,
Right.
and you got negligible
Right.
for 20 years,
Yeah,
that's something.
your
but
lifetime
it's
dose is
still-
zero. Yeah, yeah. But you're onto it, right? It's negligible, but not exactly zero,
I just
right?
wanna know the number.
It's just very close to zero. It's so low that it's not reportable for them.
I just wanna